Hello, this lecture will cover pages 1 through 9 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on basic concepts, Chapter 1A, Current and Voltage. If you take a look on, starting on page number 2, we're going to discuss the basic concepts in Chapter 1, and we're going to start with scientific prefixes. I listed all the majority of the scientific prefixes here on this table, but realistically in electrical engineering we're only going to be working from 10 to the 12th down to 10 to the minus 12. So the only prefixes that you'll be responsible for are the tera, the giga, the mega, and the kilo. And that should be a capital K right there. Notice the positive prefixes, all the positive prefixes have capital letters out here. And the milli, micro, nano, and pico. And they're represented by the small letters because they're negative prefixes. So that's a convention we're going to use. Positive exponents are going to be capital prefix abbreviations, and negative exponents will be the small prefix abbreviations. To give you some examples here on page number 3, scientific notation examples. From this point forward in your career, from this course forward, you have to start using the scientific prefixes. It's just the professional way of doing things. And here's the examples that I want you to use. 1500 volts is 1.5 kilovolt. 0.1 volts, that's 100 millivolts. 25 million hertz is 25 megahertz. And I want you to look through the rest of these very carefully and make sure that you understand the scientific notation. This is what we'll be using pretty much. We'll be using this through the entire class. On page number 4, we're going to start talking about current, voltage, and power. We're going to start out by addressing current. Current can be represented as a capital I or a time-sensitive small I. So anytime you see a capital letter, you're talking about a DC or a steady state value, and anytime you see a small representation of current, or any variable for that matter, it's time-sensitive. Current is measured in amperes. 1 coulomb is 6.25 times 10 to the 18th electrons. So if you could group 6.25 times 10 to the 18th electrons in one pow, if you will, that would represent a charge, and the charge would be 1 coulomb. The electron is a basic unit of charge, Q. The electron is a negatively charged carrier. It's a negative charge carrier. We say when 1 coulomb passes a given cross-section of a conductor in 1 second, that we have 1 ampere of current flowing through the conductor. So if you take a look, if we simply take, let's say, a conductor here, and we can take a cross-section of that. In 1 second, if 6.25 times 10 to the 18th electrons pass this cross-section in 1 second of this conductor, that's referred to as 1 ampere. Therefore, we can write an equation to represent that. The time-sensitive current, I at t, is equal to the change in charge with respect to the change in time. And if we take this delta time infinitesimally small, we end up with another equation that says the time-sensitive current is equal to the derivative of the charge with respect to time, where I is the current and Q is the charge. Or if we simply take this and we isolate Q at t by bringing delta t up and we integrate both sides, we can see that charge is the integration of the current, the time-sensitive current. That's one of the equations in the book. So when you're working out some of these problems for homework, basically if you just look at the units and you look at the definition, the the bare physics definition of current, charge, voltage, and power, you should be able to figure out how to analyze the problem. So here we have two equations. The current with respect to time is equal to the derivative of charge, dt, or the charge is equal to the integral over time limits of the current. On page number 5, I mentioned just a minute ago, but you have direct current or voltage waveforms, and they're represented by capital letters. I for current, V for voltage, where I or V is a constant and looks like this. The ordinate axis here is equal current, either current or voltage, and you have time in this abscissa axis here, and in this case right here we're showing a fixed voltage or current, a constant voltage or current of 10 amps or 5 volts or whatever we want to label this scale. Alternating current or voltage waveforms are shown by small letters, I a t or V a t. When you see small letters in this course, it's time variant parameters. And here's a time variant parameter for either current or voltage. We know that's a sinusoidal waveform defined by a period, which we talked about in a previous class. It has a peak value from this 0 volts reference. It's a symmetrical waveform, so there's our 0 volt reference right there. And wherever this goes up to, let's say this goes up to 10 volts. And let's say it goes down here to negative 10 volts. Then in this case right here, our peak voltage VP is 10 volts. Our peak to peak voltage is 20 volts. We'll talk about RMS values later on in the semester. And notice we have our time axis here. Period is defined by the repetition of the waveform. And the frequency formula, which is a very, very important formula, frequency is equal to 1 over the period, where frequency is in hertz and period is in seconds. The period here is in seconds, or units of seconds, microseconds, milliseconds, and so forth. Very important equation, one of the basic equations in electrical engineering. Conventional current flow versus electron flow on page number 6. If you take a look, here we have a source of EMF, a battery, and we have one resistor, and we have a simple series circuit here. And it's a series circuit because the current in the circuit is the same. So no matter what point you pick in this circuit, the current is identical. Well, we're going to discuss two different conventions. We're going to discuss a conventional current flow, where current flows from the positive terminal of the battery to the negative terminal of the battery, and we're going to talk about electron flow, where current would flow from the negative terminal of the battery to the positive terminal of the battery. Most universities use conventional current flow, and we're no exception. This course will study conventional current flow, and we'll use that convention. If you're in military schools, a lot of military schools, if you're in the service, they're training technical schools use electron flow. But it's the same thing. Basically, conventional current flow and electron flow are the same thing. It's just looked at two different ways. You're looking at it from one side, you're looking at it from another side. But it's identical. And I'm going to discuss that right here. If you take a look, we have electrons built up here on this, negatively charged carriers built up on this side of the battery. There's electrons down here. Up here, there's an absence of electrons. Absence of electrons are referred to as hole charges. So you have hole charges and you have electrons. Well, some people say, well, electrons are for real and hole charges are not. Well, some physicists will disagree with you. Some physicists will say that if you have electron charges, they're real, and hole charges are every bit as real and tangible. So let's take a look at what these electrons do. I put a bunch of electrons on a certain point of the wire down here. And I want you to notice that we have a hole charge over here. And as these electrons move over, or are pushed away here, and they're attracted to these hole charges up here, the electrons go this way. And you can see this electron goes over here and it makes this a hole here. Then this electron moves over to here on the wire and it makes this a hole. Then this electron moves over to here and it makes this a hole. And then this electron here moves over to there and it makes this the hole. So I want you to notice what these electrons are doing. they seem to be migrating from left to right. In other words, the electrons are moving this way, but look at these holes. This single hole charge is moving from right to left. It's moving in this direction, opposite direction of electron flow. Electron flow always goes from minus to plus, where the electrons are the majority charge carrier. However, this is the one we care about. It's the one we're going to use the most. Conventional current flow always goes from plus to minus, right up here. It always goes from plus to minus. That's the convention we're going to use. Where the holes, the positively charged holes, are the majority charge carrier. Note, this course uses conventional current flow. Don't get any serious discussions about the differences between conventional current flow and electron flow. 6 of one, half dozen the other. It's just two different ways of describing the physics. On page number 7, we're going to talk about voltage. Capital V is steady, is constant. Time variant is a small parameter, V. It's measured in volts. It's also called electromotive force, EMF. When you hear of EMF, it's electromotive force, and it's a source of voltage. Or they call it potential. So here's the physics of it. If it takes 1 joule of work, that's energy, to move 1 coulomb of charge, and we know that's 6.25 times 10 to the 18th electrons from one point to another, then the 2 points have a difference in potential of 1 volt. Therefore, based on this description, the units of voltage are in joules per coulomb. If you read this, you'll see that the units of voltage is in joules per coulomb. EMF is a potential difference that does not decay as charges are transferred from one point or terminal to another. So if you take a particular circuit like this, and let's say this is 20 volts here, as these charges move, as these whole charges move around clockwise in this loop, that stays at the same voltage, 20 volts, whatever it was. If it's 10 volts, it stays at 10 volts. If it's 20 volts, it stays at 20 volts. The charge motion around that loop has nothing to do with that voltage changing. It stays constant. Different symbols of sources for voltage. You might see this, showing plates of a battery, or multiple plates. They might have additional plates, but that's a simple symbol for a voltage source. This is a simple, you'll see this as well. And you'll see the time variant, the small v sub s, the source voltage shown like this. These are 3 different symbols that are all going to represent voltage sources. And you'll see them in the homework. Potential difference versus EMF. We will use the series circuit below to explain the difference between potential difference and EMF. Here we have a simple series circuit. Notice there's 3 resistors. So here's the source of EMF of 100 volts. E is the source of EMF, and the following voltages V are the potential differences across each resistor or combination of resistors. So if we look up here and we're discussing this circuit, V sub A is 100 volts. Well, if this is a ground reference point, that's where we're going to measure everything from. That's going to be your reference point down here. It's usually going to be in the bottom of the circuit like this. You're going to draw a ground symbol. That's your reference point. Notice that the voltage at this point, if you're at ground here, you're up 100 volts. So VA is 100 volts. This is the voltage across the source of EMF with respect to the reference point of 0 volts. Right here. 0 volts is right there. That's your reference. What about VR1? What's the voltage VR1? Well, VR1 is equal to VA. As current flows down through this is the direction of current now. We already discussed that. Flowing down, it flows with a plus to minus polarity. That's called passive sign convention we're going to talk about next. So you take the voltage here, and you subtract the voltage at this side. So VR1, the voltage across this resistor, is VA minus VB. It's 40 volts. Look at the circuit. What about VR2? What's the voltage across that resistor? What's the voltage at the most positive point? VB minus VC. It's 50 volts. What's VR3? It's VC minus 0. It's 10 volts. Look at the circuit when you look at each of these equations. VC is simply equal to VR3. It's 10 volts. VB, what about VB? VB is equal to VR3 plus VR2 is 60 volts. What's the voltage here at VB if you're at this point? Well, you're at ground here, and you come up here, and you come up here. That's how I'm getting the VR3 plus VR2. That's 60 volts. And what about VA here? Two ways of looking at getting VA. You could go up this side, or you could go up this side. If you go up on this side, it's VR3 plus VR2 plus VR1. So if you could add, if you take a look at the voltage drop here, the voltage drop there, and the voltage drop there, and you add them up, you'll see you'll get 100 volts. Or simply, if you go from this side, you're up 100 volts. Either way, you're going to get 100 volts. At the top of page, this is on page 9. At the top of page 7, we define voltage as work in joules per charge in coulomb. At the top of page 7, we define voltage as work in joules per charge in coulombs. Therefore, the equations are voltage, time-sensitive voltage, is equal to the derivative of work with respect to charge. Look at the top of page 7, and you'll see how we take the words and we put them in terms of an equation. That's the change in work or energy divided by the change in charge. And we know that the current is equal to dq dt. Therefore, since we know that the current is equal to dq dt, we can bring dt up to this side, integrate both sides, and you can see that charge is equal to the integral between these limits of the current dt in coulombs. We discussed that before. So in this lecture we discussed scientific prefixes, and you're going to use those from this point forward. We got into the details of current, and we got into the details of voltage. That concludes this lecture.